I'd now like to add one last example of a group to our lengthy list at this point in time. I'd like to generalize the specific example that we did in the previous video. So I'd like to prove the following lemma. For a fixed modulus n, so that's just a non-zero integer, let's say a positive integer. The set of positive integers less than n and relatively prime to n, which we're going to denote again by u of n, forms an abelian group under multiplication. So that's the lemma we'd like to prove. And I'd like to talk a little bit about the theory of this proof. It should really be straightforward. In order to prove that the set u of n forms a group under multiplication, and of course by that we mean modular multiplication here, we're going to have to prove that it satisfies the four axioms necessary to form a group. So we're going to have to prove that the group operation is closed, that the group operation is associative, we're going to have to exhibit a multiplicative identity, and we're going to have to show that every element of u of n has an inverse. That's what we have to do just to show that u of n forms a group. To show that u of n forms an abelian group, we're going to have to show that our modular multiplication is commutative. Now, some of these tasks are going to be easier than others, and this is part of the reason I want to do the proof of this fact is that I think the proof is a very characteristic example of how these proofs go in establishing that something is a group. So let's begin here. The first thing that I'm going to do is show that the set u of n is closed under modular multiplication. This, as you can see, the proof of this takes up at least all of this slide and some of the next. And so we could reason maybe that showing that u of n is closed under multiplication is somewhat difficult. And that is often the case. Showing that the set that you have is closed under the operation is often one of the harder things to prove about a group. The rest of the three of the other properties showing that there is an identity, that the operation is associative, and in this case showing that the group is abelian, those three properties will be relatively easy, and then exhibiting inverses will be somewhat, slightly more difficult. And that tends to be the case. That's a very standard example in proving that something is a group. Closure and inverses are typically the hardest, and the other of the group axioms are often easier. So let's begin. Let's show that u of n is closed under multiplication. What this means is I need to take two elements starting in u of n. I need to combine them and look at the output under my operation, which here is modular multiplication, and I need to show that that result belongs to u of n. That's what I need to do to show closure. So that's the first thing I've written down in my proof is let's start out by taking two arbitrary elements of u and n, call them a and b, and let's show that their product ab, when I look at it modulo n, belongs to u of n. Now the first thing that I want to show is that this number ab is relatively prime to n. And then I will work on, right, so we're doing modular multiplication. When I look at ab and I take their product, it may be bigger than n, in which case this product ab might not belong to u of n because it's just too large. So what I would have to do in that case is then reduce ab when I, modulo n, and show that that product belongs to u of n. So the first step in doing this is just to show that the product ab, even if it's too big, is relatively prime to n. So to do this, let's start with what our assumptions are. We picked ab. They're not just arbitrary things, they belong to u of n. What this means is that they're positive integers, they're less than n, and they're relatively prime to n. What we're going to use is the fact that a and b are both relatively prime to n, and because a and n and b and n are coprime, which is this since statement right here, we've seen that we can write their greatest common divisor, which is 1, as a linear combination of these two things. So a and n are coprime, and therefore 1 can be written as as plus nk, and in a similar way, 1 can be written as bt plus nl, where the new letters that I've introduced, s, k, t, and l, are all integers. Now what I'm going to do is I'm going to take the first equation, 1 equals as plus nk, and I'm going to multiply both sides of that equation by b. And when I do that, I'm going to get this somewhat messier equation. I'm going to find that b is equal to ab times s plus nb times k. From that first equation, I'm now going to substitute it into my second equation. So my second equation up here is that 1 is bt plus nl, and where I see that b in that equation, I'm going to substitute in this much more complicated expression for b, abs plus nbk. When I do that, when I make that substitution and then simplify all that arithmetic and move terms around, I find that the number 1 is AB times the quantity ST plus N times the quantity BKT plus L. So it's a little bit messy, but here's the important part. On one side of the equation I have the integer 1. On the other side of the equation I have AB multiplied by the integer ST, and then I have N, which is multiplied by the integer BKT plus L. So what I've done is I've shown that 1 can be written as a linear combination of AB and N. And what this means is that AB and N are relatively prime, which was the first step in showing that U of N is closed. This is the first thing we needed to do, and at this point in time, we've done that. And the reason that we have that AB and N are coprime is because I can write 1 as a linear combination of the two of them. All right, now let's continue. In order to continue, I'm going to use, I now know that AB is relatively prime to N, but what I really want to know is that when I take AB and reduce it modulo N, which is the result of combining A and B under the actual operation I've given, I want to know that when I look at AB mod N, that that's relatively prime to N, and that's going to help me determine that the product AB mod N belongs to U of N. To do this, we're going to recall something that we've done before, which is that when I take the greatest common divisor of two numbers, in this case, AB and N, this is going, if I were to write AB as a multiple of N plus some remainder, then the greatest common divisor of AB and N is equal to the greatest common divisor of N and the remainder when I take AB and write it according to the quotient remainder theorem as a Qn plus R. That is, the greatest common divisor of AB and N is equal to the greatest common divisor of AB mod N and N. And this is exactly what we wanted. So at this point in time, what we've shown is that if I take A and B inside U of N, and I combine them under modular multiplication, that I get something relatively prime to N, and because I've looked at the operation mod N, it's less than N, and that's exactly what we needed to show. By definition then, AB mod N belongs to the set U of N, and we have closure. All right, so at that point in time, once we've finished closure, as I sort of hinted at before, there are a handful of other things we need to do. We need to show that this multiplication is associative. We need to show that the group has an identity, and because in the lemma I'm claiming that I have an abelian group here, I'd like to show that my operation, which is modular multiplication, is also a commutative operation. And I've done this all at once. All three of these properties are relatively simple. What we're going to do is use the fact that we know what the multiplicative identity should be, and we know these facts about the operation because this is a very natural operation. So here what I've done is I've asserted that the number 1 is the identity of U of N. It certainly belongs to U of N. It's less than or equal to N, and it's relatively prime to N, so long as N is not 1. And multiplication is certainly an associative and commutative operation, because we really know this. We really and truly know this about addition and multiplication, and we're very familiar with this number system. So we know that regular multiplication is associative and commutative, and when you add in this modular component to the operation, you don't lose that, and that's something that we studied back in the slides when we studied modular arithmetic. You can show very easily from those properties of doing modular arithmetic instead of normal arithmetic that you're not going to lose associativity and commutativity. So we get associativity and commutativity somewhat for free because we know these facts about regular, plain old addition and multiplication. And we have that 1 belongs to U of N, and it's going to be the multiplicative identity because it is the multiplicative identity of sort of standard number systems. So identity, associativity, and commutativity, we write this down, we show that we've thought about them, but we don't really have much to check. We kind of inherit these properties from the fact that we've known them before. The very last thing that we need to do to finish off this proof is we need to show that inverses exist. So again, we're going to have a little bit of a runaround. I think what we're going to do is first show, we're going to take A belonging to U of n, and then we're going to show that it has some sort of multiplicative inverse, and then we're going to find that it has a multiplicative inverse sort of in the right range. So let's begin. Let's take A, which is an arbitrary element of U of n, and let's find an inverse for it. Again, by definition, A belonging to U of n means that A is an integer and that it's less than or equal to less than n, and it's relatively prime to n. So let's use this relatively prime assumption in the standard way that we have been so far, which is to take 1, the GCD of these two numbers, a and n, and let's write it as a linear combination of a and n. So as we did before with closure, let's take 1 and let's write it as as plus nk, where s and k are integers. Now, this is a statement of equality over normal operations inside the integers. 1 is equal to as plus nk. What I'd like to do next is take this equality, and I'd like to look at both sides modulo n. So I'd like to reduce 1 modulo n. That's really easy. It's just 1. And then I'd like to take the right-hand side of this equation, as plus nk, and I'd like to view that modulo n. Now, I don't really know what happens to as. As I'll just leave sitting there as it is. No pun intended, but that's hilarious. And what happens to the nk piece is that nk is a multiple of n, which means that if I wrote it as a quotient and a remainder, the remainder would be 0. And so if I reduce this as plus nk modulo n, I would have as plus 0, and I'll just write that as as. So 1 equals as plus nk. When I read that as a congruence instead of an equality, I find that 1 is congruent to as modulo n. Now, the next thing I'd like to observe, which is a little bit tricky, is that this number s, whatever it is actually co-prime to n. The reason that this holds is if I go back to this statement, 1 equals as plus nk, A is an integer just as well as s is, and so in a way, if I view s and n as the special numbers and a and k as the sort of placeholding numbers, I've exhibited that I can take 1 and I can write it as a linear combination of s and n as well. So switching the roles of a and s in this equation, I have that 1 is equal to sort of sa plus nk, and that means that s and n are relatively prime. That is, their greatest common divisor is 1. And again, that's because we can write 1 as a linear combination of s and n. How? This linear combination right here. We don't know where s lives, sort of a priori. S could be any old number in the world. I didn't specify where it lived when I wrote 1 equals as plus nk, so for all I know, s is really, really huge. So s may not immediately belong to the set U of n. However, when I take s and I reduce it modulo n, that is going to, when I replace s by its remainder mod n, that is going to be a number less than or equal, strictly less than n. And again, using the same logic as we've used before, that we used when we were working on closure, because s and n are co-prime, when I take s and reduce it modulo n, the GCD of s and n is equal to the GCD of s mod n and n, and therefore the number s mod n is going to be co-prime to n and strictly less than n, and it's an integer. So s mod n belongs to U of n, and it's going to act as a multiplicative inverse for a. If I replace s by s mod n, or simply just break up this equivalence here as the quantity as mod n as a mod n, s mod n, then I have what I want. So altogether, this finishes off the proof of this lemma, since we have shown that we have closure a multiplicative identity, associativity, and commutativity of our operation, and we have inverses, and this shows that U of n forms an abelian group under multiplication no matter what n is. And this is a good example of a collection. This is a good example of a group, a finite group, that we'll be working with quite frequently.